So what we're trying to do when we do data-driven decision making is we're trying to make claims. And this is the same thing whether we're trying to make scientific claims or just trying to make statements in everyday life. The idea is that we're putting forth some kind of statement whose truth we want to be able to verify. So we're concerned about the truth of our statements, and this proves to be surprisingly difficult. Even leaving aside larger issues about bias and argument construction and logical fallacies. There are all kinds of issues, even that we've already seen, having to do with sampling error and even numerical problems that come along with the very nature of random variables. So there are all kinds of hazards that stand between our ability, between our statements and their truthfulness. And what we're trying to do then is to make as truthful a statement as we can. And there is a philosophical theory that helps us kind of come up with a procedure that allows us to have the best chance of making a truthful claim. And so there are a couple of kind of underlying truths that seem to come up again and again that kind of undergird this entire process. One has to do with how it is that you can prove something. So here's a quote from Albert Einstein. He says, "No amount of experimentation can ever prove me right, but a single experiment can prove me wrong." And this became more formalized by a philosopher named Karl Popper in a falsification principle. And the way this works is just that it turns out that it's we can't prove that something is true. We can only prove that a particular statement. We can only prove that a particular statement is false. So the basic idea is, if we want to be able to make a claim, then we have to be able to invert that claim into its opposite and then prove the opposite false. Now, even that only goes so far, because all you're able to say is that you've either proven it false or you have not proven it false. That doesn't necessarily mean that you've proved the inverse true, but it kind of is a step along the way. Okay, so one of the principles that we have here is this idea that we want to start off by saying that we want to come up with a starting claim, and our process is going to be to see if this particular claim is false. Okay, so that's the first thing. The first kind of theoretical lesson that we'll use is we want to try to prove something false. So to prove something false. And the second thing we need to do is we want to just minimize the probability that whatever conclusion we make, minimize the probability that our conclusion is wrong. Now, we have to kind of acknowledge that the reality of most things is we have to put a number on our level of certainty. But we want to make sure that whatever conclusion we draw, that given all of these various things that can go wrong, that we have minimized them. So we have a procedure then called hypothesis testing, which gives us a way to minimize the probability that whatever conclusion we draw is wrong. And it also fulfills this idea that we need to be able to prove something false. Okay, so what we need to do then is to stay fairly close to this. We've got a 6-step procedure here, and I don't want to sell it because this sounds like kind of one of those tacky, self-improvement commercials. But we can look at this as a 6-step process that has been proven to be effective at getting at the truth of a claim. Okay, so I'm going to stick pretty close to this 6-step process and just go through step by step. And toward the end of the lesson, I'm going to give you an example and show you how to go ahead and put the 6-step process in action. Okay, so what we want to do first then in implementing this under hypothesis testing, and there are actually two. I don't know if I'm going to say too much about the other one, but we're going to see in detail. I'm going to use the critical value method, but in addition to the critical value method, there's also the p-value method. But we're going to start off by looking at the critical value method. Okay, so the 6 steps then, let's just take them in order, and I'm going to go into detail as I go along them. Okay, so in step 1, you have to state the null hypothesis and the alternative hypothesis. Okay, so there are 2 hypotheses here that you have to state. So H0 or H sub naught or H naught. This is the one that we're going to target to see if we can prove false. So this is our null hypothesis, and the way you state a null hypothesis is to use H sub naught. Okay, and sometimes it's H sub n or something like that, but usually you'll see it denoted like this. Okay, so you indicate that your null hypothesis is with that H sub naught, and then use a colon here, and then your null hypothesis is going to be a claim about the value of a population parameter. Okay, so that's important. So it's going to be a Greek letter here. Usually we're going to be making the null hypothesis about the mean, but it could also be about the proportion, which is mean or proportion or variance. But it is a claim about the population parameter. Okay, now remember that the sample statistic is just an estimate of the population parameter. So we're actually making our hypotheses about the population parameter. Okay, so then we're going to have some kind of equality operator here. Now the null hypothesis is always going to contain equals, so it's going to be equal to or less than or equal to or greater than or equal to. But there's going to be some kind of value here. This could be 0, could be 5, whatever it is. So our null hypothesis has to be labeled like this with a colon, the population parameter we're making a claim about, and then some kind of equality operator. Okay. I have actually seen null hypotheses in the past where I've given a blank and said put the null hypothesis here, and then somebody just wrote like 5. Okay, so remember that a null hypothesis is a claim, and it has to include equals. Okay, now the alternative hypothesis, which can either be H sub a for alternative or H sub 1, either way is fine, but we're gonna put down that label, and then this alternative is always going to be the opposite of whatever is over here. Okay, so the opposite of population mean equal to is just going to be that the population mean is not equal to that. And I'm going to go into the implications of all these various alternative hypotheses in a minute. But for now, just note that this is the opposite. Okay, so okay, these are all alternatives that go along with this particular null. Now, so what is the opposite of mu less than or equal to something? So the opposite of less than or equal to is mu greater than that value. Okay, and over here, this is going to be the opposite of greater than or equal to is less than. Okay. All right. So this is what the null hypothesis and the alternative hypothesis statements should look like. Okay. So just don't forget that the null has to contain some kind of equals. Okay. So I want to have a little bit of practice here and just show you how you construct these hypotheses, because it can seem a little bit backwards because you're having to start off by putting up a hypothesis that is the opposite of what you're trying to claim. So sometimes it is helpful to form the alternative hypothesis first and then step up backwards and do the null. So let's take a look at some kind of business real world examples of where we would do this. Okay, so we've got some machine on our shop floor, and the documentation from the manufacturer says that it will run 60 days without requiring any maintenance. And you want to test this claim. Okay, so this is the claim that we want to test. So our null hypothesis then could just be, okay, so write down h sub 0 colon, and I'm going to have to take a sample, right? So it's not enough to just look at a single machine run. We're going to have to take a bunch of them, and then we're going to take a look at the average number of days. So it's going to be, we're going to see if we can prove this false. Okay, so if this is the null, then the alternative is just going to be that it's not 60. Okay, there's nothing in the problem that says that we have a suspicion one way or the other. So we don't really have a directional hypothesis. All we're interested in testing is whether it's not equal to that. Okay, so these are our hypotheses. Okay, so let's take a look at another example. You run a branch of a delivery service, UPS, FedEx, whatever, and you suspect that deliveries are taking longer than they used to. And they used to take an average of 6 hours. Okay, so notice that we're starting off with something that we think we want to try to prove. Okay, we suspect that they're taking longer than 6. Okay, so let's write the alternative hypothesis first. So H1 then, we're going to say, now again, we can't just look at a single delivery, we have to do an average. And so we're making a claim about the average. So the average, we think it's might be taking longer than it used to. Okay, so we are saying that it's greater than 6. Okay, so now we can step backwards and form our null and say, well, what's the opposite of this? Well, the opposite of greater than is just going to be less than or equal to 6. Okay. All right, let's look at one more example to get a little bit of practice and a little more practice on hypothesis formation. Job satisfaction appears to have dropped among your employees. You administer a job satisfaction survey, and this is a well-tested, well-validated instrument for gauging satisfaction, job satisfaction, which consists of 36 questions, each of which has 6 points. Okay, so you give this test, and you're concerned, you have a suspicion that the job satisfaction has dropped. Okay, so now notice that again we have a direction of these hypotheses. So our first, our alternative hypothesis then is going to be that the average job satisfaction is less than it used to be, which was 148. Okay, which makes our null the opposite of this, which should be greater than or equal to 148. Okay, so we want to see if we can disprove this. Okay, so our original suspicion, the reason that's driving the investigation in the first place, is that we're concerned that it's dropped. So we want to conduct a test that it is below. And so if we have proven that, if we've confirmed, or if we fail to reject that it's greater than or equal to 148, that does answer our question, but it doesn't address this initial idea that we're trying to confirm whether it's dropped or not. Okay, so all right, so there's forming these hypotheses. Now, the alternatives are going to be determined by what your nulls are, as in those examples that I just gave. Now, I have put up I've put up some more detailed videos on how to go about finding these particular critical values here. But for now, I just want to show you, make you aware that if you have a null, I'll put the nulls over here. So if we have the null, the H0, so the null hypothesis that corresponds to an alternative of greater than is going to be that it's less than or equal to whatever that value is. Okay, so what you so we're going to be trying to reject if we have a value out here. Okay, now in this case, so that's going to be a right tail test. Okay, so if we find a value that is out here, we will be rejecting that it is less than or equal to. Okay, so if we have a value out here, then we're going to be rejecting the idea that it could be less than or equal to. And it looks like it's 0 here, so I'll just put the 0 right here. Okay, so that's a right-tailed test. A left-tailed test, so notice here the alternative is that the mean is less than something, and we'll just write in 0 because it does look like 0 is there on the diagram. So in this case, the null was that it's greater than or equal to 0. Okay, so you see, if we wind up with a test statistic that's down here, we can very safely reject that it's greater than or equal to 0. Okay, and over here, so with a two-tailed test, the alternative is just that the mean is not equal to a particular value, and so that meant that our null was that it was equal to 0. Okay. Okay. So there's 3 different tests that we might be doing. Really, these are going to have the same critical values, just with different signs. So it's just these are the one-tailed tests, and that's as opposed to our two-tailed test. Okay, so that's all step 1, forming the null and alternative hypotheses. Okay, so step 2 then consists of 2 parts. We're gonna choose a level of significance called alpha and a sample size n. Okay, now this sample size, there is an entire discipline for determining exactly how big your sample needs to be. In the real world, usually you're driven by cost concerns or convenience, and for the purposes of this class, this is going to be given, by the data that's available. We're not going to be gathering data, but just know that there's a whole way to calculate the size of sample that you need, and it's going to be some function of how sure you want to be, the effect size that you're looking for, how much variability there is in your population. So there's some kind of worksheet that you can fill out to figure out, okay, what's going to be my ideal sample size. But for now, we just say, okay, this is our sample size, and I think in our example coming up, that might be something like 100. Okay. Now this level of significance, which is denoted with the Greek level alpha, this is our desired level of certainty. So if we say, okay, I want to be given the actual, setup of the test, how sure is it important for you to be? And in most cases, 95%, a 95% confidence level, 95% confidence level means that we are going to set alpha. Alpha is going to be equal to 1 minus our confidence level. So that means in this case, our alpha, so I'll put alpha over here, and this is our confidence level. So 95% confidence level means we have an alpha of 0.05. And what this describes is our acceptable possibility of error. Acceptable, and it is a probability, so acceptable probability of error. Okay. So when we set alpha equal to 0.05, we are saying we are okay with a 5% chance of being wrong. Okay. And so another typical confidence level is 95%, which means you have an alpha of 0.1. In physical and biological sciences, sometimes you want to be 99% sure, like drug testing and so forth, and then you have an alpha of 0.01. But unless otherwise stated, I and the rest of the world are interested in a 95% confidence level, and therefore an alpha of 0.05. Okay, so step 3 then. Determine the appropriate test statistic and sampling distribution. Okay. Now, in another video, I went over the central limit theorem, which, among other things, told us that our sampling distribution of a measured random variable is going to approximate the normal given a decent n, so given a decent sample size. So we can assume a normal distribution if we have an n of greater than or equal to 30. Okay. Now we can also say that our sampling distribution will be normal if we know the population standard deviation. Okay. So if this is known, and I'll tell you this much, it's almost never known unless I'm giving it to you in a problem. But if the population standard deviation is known, or so either of these, so n is greater than or equal to 30, or our population standard deviation is known, then we just state that our sampling distribution will be normal. Okay. If those are not true, then we can use the t distribution. Based on a certain number of degrees of freedom. And I go over the t distribution in another video also. Okay, so, but what we mean by sampling distribution is, is it going to be normal or is it going to be the t distribution? Now, the appropriate test statistic, this is going to be one of the tests that we go over. So this is, in the case of, if we have a normal sampling distribution, then we're going to use a z statistic. If we don't have these things and we use the t distribution, then we're going to say we're going to use the t statistic. We'll see in later tests that we're going to have a chi-square statistic, and we're going to have an f statistic. But on this step, so on step 3 of the hypothesis testing, this is what we need to state. So it's either going to be a z statistic, a t statistic, chi-square statistic, f statistic. So we're simply stating what the appropriate test statistic is, and then stating our assumption about what the sampling distribution looks like. And I had another video on sampling distributions. Okay, so there's step 3. So step 4 is to determine the critical values and divide the rejection and non-rejection regions. Okay, so I had another video on critical values, and if you're not clear on critical values, then it'd be a good idea now to go ahead and check that out. But the idea is that under the null hypothesis, we're stating that the truth of the matter that we're testing is that the population mean, let's say, is equal to 0. And we're saying that if that's the case, and it's a normally distributed variable, then it's going to look like this. It's going to be, most of the values are going to be near 0, give or take a little bit, and 95% of the time, so the height of this density function indicates, the frequency that we observe these values. So that means this area in here and so in this range right here, 95% of the time we're going to observe a sample X between here. So let's say this is, -2 and +2. Okay, so the null hypothesis is going to state that it's equal to 0, and we don't, it's not enough to just say that it's different from 0. It has to be significantly different from 0, and 95% of the time, if it is 0, then it's going to be between here. So if it's going to if we have 95% of the area here, that means we have leftover 5%. We have 2.5% here and 2.5% here. Okay, so 2.5% of the time we're going to get a sample statistic that's out here, and 2.5% of the time we're going to get one down here less than -2. Okay, so even if the true population mean is 0, 2.5% of the time we're going to get, just because of sampling error, we're going to get something that is less than -2. Okay, so this is the point of the critical values. The critical values are telling us, okay, if we want to be 95% sure, then we are drawing a line right here and saying we will only reject the null hypothesis if we are out here beyond this 95%. So if the chances are less than 2.5% that we get this value, let's say we wound up with a 2.2, okay, there was less than 2.5% of a chance of getting a value like that if the null is true, so therefore we reject. Okay, so that's what we're doing. We're trying to find, what are these border values here that are, that enclose 95% of the area of this density. Now, remember that, so in order to find these, you can use this. I think that if you want to use your calculator, the function is called inverse norm, but in Excel we use norminv. And so this will find the right tail. This will find the right one. Because remember that the default behavior of this normin function is to calculate from -infinity up to this area. And so this 95% plus this 2.5% brings us up to here. So that's why we put in 0.975. Okay, and this turns out to be, so this critical value is 1.96. Okay, so this is what we do with if we're using a normal distribution. Now, as I said, if we don't know the population standard deviation, or if we have a small sample size, then we need to use the t-distribution, and that critical value is found with t.inv, and you use the same number here because we're trying to get this value with 97.5% of the area to its left, And this is the degrees of freedom. And I went over that in that video also. So if the degrees of freedom in these two distributions and critical values are not clear, then I would encourage you to go and look at the Finding Critical Values video. Okay. So the idea is that we just say, we state what these are. If we find anything outside of this, so for a two-tailed, because we're making two critical values here, anything in here or in here, so anything greater than 1.96 over here, or less than negative 1.96 over here, then we are going to reject. Okay, so that's what the critical values are. Okay, all right, so there's step 4. So in step 5, then, we collect the data and compute the value of the test statistic. Now some people think that this is like the main part, and they just do this part and ignore, the 4 parts that came before. But as I emphasized at the beginning, there's a strong reason for all of these steps, and it's because each one needs to be addressed for its potential failures individually. So we need to make sure that we're going step by step as we do this. Okay, so in the case of in the case where we've been able to assume a normal distribution and we're using a z statistic, it's calculated this way, and this is the one that we're going to use in our example. So this is our sample mean. This is our hypothesized mean. Okay, so if we under our null, we were saying that it's equal to 0, and in our sample mean, we observed negative 0.5, then this numerator would be negative 0.5 minus 0 over, and this should look familiar. So this is going to be the standard deviation of the population. Notice that it's just the Greek letter. Remember, standard deviation of the sample was just an S. So we need to know the standard deviation of the sample to use this, and that was part of the normal. Okay, so so then we just divide that figure by the the square root of the sample size. Now, if you're putting this into a calculator and you want to do it in one step, be sure to use parentheses, because if you don't, then you're going to get burned by order of operations. So use parentheses like that. Okay, make sure that the denominator is calculated. Okay, so we'll see that this is for the normal. If we don't have the conditions to assume a normal distribution, that is, we have to use the t distribution, then we are going to use, and let's see if you can see what's different here. Okay, sorry about that. This is, let me get my, okay, so the only difference here, if we're using a t distribution, and remember n, so if our n is less than 30, then we use this. Now, this is, so if we're going to look up the critical values on the normal, so we're going to use norm dist, then our population standard deviation has to be given us. Now, the only difference between these two is that this is our sample standard deviation. Okay, and we look up we look up this. So if we have to use the sample standard deviation, then we're going to use, look up those critical values with t.inv. And if we have the population standard deviation, we can use norm.inv. Okay, so in our case, we've only looked at the z and the t, but those are the two test statistics that we'll be calculating. Okay, so that's step 5. Now step 6, make the statistical decision and state the managerial conclusion. So these are two different things. This only has 2 values. This can only be reject or fail to reject. Okay, so if our test statistic, so if, let's say we're doing z, so if our z test statistic is if our z statistic was in the rejection region, that is, it was beyond the critical value, then we're going to reject. Okay, if the z is not beyond the critical value, then we fail to reject. Now it's important that a failure to reject is really just saying that given the evidence, there's not sufficient evidence to reject it. So philosophically, we haven't really proven that it's false. We've only just in this particular experiment been unable to prove that it's false. Okay. Now, so these, as I said, these are two different things. The statistical decision is just reject or fail to reject. So that's a very rigid standard of how you state that. But the managerial conclusion is the more broader. That's the interpretation. So this could be something like employee satisfaction has gone down, or the machine does not go for 60 days without requiring maintenance. Or so it's raising the statistical conclusion up into its original problem context within the business. Okay, all right. So that's all 6 steps. Now, if any of these are unclear, hopefully, as I work through the next problem, some of your questions will be answered. Okay, but we're going to go ahead and tackle a specific problem that's the kind of thing that quality control would have to actually do, and quality control does do quite a lot of hypothesis testing. Okay, we want to test the claim that the true mean diameter of the manufactured bolt is 30 millimeters. And we're given that we're going to assume, notice the Greek letter, so it's a population standard deviation of 0.8 of a millimeter. Okay, so we're told to test, so we need to go through all 6 steps, and we're going to do that now. Okay, so step 1 then is to state the hypotheses, the null and the alternative. Okay, so the null hypothesis then, once again, we're making a claim about the average, right? We're not concerned about one bolt. We want to know what the average. So, we take a sample of, let's just say we're going to take a sample of 100. We've made a population of 10,000, but we're only testing 100 of them. And we are claiming that the average among that entire population is 30 millimeters. Okay? Which would make the alternative hypothesis the opposite of that, which is just that it is not 30. Okay? So we're on to step 2. Okay. we need to specify the desired level of significance and choose the sample size. So I'm just going to say, most of the time this is going to be given. We'll just say, okay, sample size, we're going to take 100. And you can see how in a case like this, this would be determined by, cost factors. The time required to sample those versus the risk and all that. Okay, and so the desired level of significance, as always, if it's not given, then assume an alpha of 0.05. So we want to be 95% sure that we are right. Okay. Okay, step 3. Determine the appropriate test statistic and sampling distribution. Okay, so we've got a sample of 100, right? And we are also given the population standard deviation. Okay, so we're going to be able to use, we're going to be able to say that this sampling distribution is going to be normal, which means that we are going to be using a z statistic. Okay. All right, so we're already up to step 4. Okay. Determine the critical values. Okay, now what's going to determine these critical values? Okay, once more, I'm just going to sketch out what we have here. We've got under the null hypothesis, the mean is 30, and beyond some values, let's say, I don't know, maybe standard deviation is 0.8, maybe beyond like 32 or something, or minus 32. Beyond these values, we're going to have it's going to be very unlikely that the actual mean is 30. Okay, but we're going to be dealing with a standard normal, so this is going to be expressed as a number of standard deviations. So all I need to do is, in order to find my critical values, I'm going to use the norm in function in Excel. And we have said, so we know it's a two-tailed test, so we have 2 areas here, and we know that we have an alpha of 0.05, so that means with 2.5% of our area here, 95% here, this percent, that means this is going to be the critical value corresponding to 0.99, sorry, wrote that wrong, 0.975, okay, and we're going to use a standard normal with a mean of 0 and a standard deviation of 1. Okay, and we'll go ahead and do that. We've already looked this up before, but let's just go ahead and do it. Okay, so this is going to be norm in 0.975, mean 0, standard deviation 1, and yeah, okay. Okay, so 1.96. Okay, so that means we're going to have a positive 1.96 here, and because this is a two-tail, we're going to have negative 1.96 here. So if we have anything that is greater than 1.96 or less than negative 1.96, then we know that we can reject the null that is equal to here. Okay. Okay, so the next step then. So step 5 is collect the data and compute the value of the statistic. Okay, so let's go back and revisit what we're given here. Okay. So we're not actually given the sample. So I guess we are supposed to assume a certain sample average. So let's say that we've taken our sample of 100 and we've gotten 29.84. Okay. All right, so this, if you looked at the other slides, that value was in there, but it wasn't in my particular one here. So, okay, so our sample then, we've collected our 100 samples and found 29.84. Let's go ahead and put that in there. Okay, so just to review, so we got N was 100, and our sample mean was 29.84. Okay, so remember that our null was about whether it was equal to 30, and we're dealing with millimeters here. So if you observe something like this, you would say, well, that's awfully close to 30. So it's kind of hard to know right away whether to reject. And remember that we're given a population standard deviation of 0.8. Okay, and so I'm going to go ahead and write the formula for the z statistic again. So you calculate this as x bar minus hypothesized average over the standard error of the mean. Okay. So notice that what this is saying is it's seeing how far your sample is away from your hypothesized mean in units of standard errors. Okay. So let's go ahead and just plug in then. We got 29.84. Okay. Minus 30 over 0.8 over square root of 100. Okay. And all told, this winds up being negative 2.0. Okay. Okay, so we've calculated the value of the test statistic. Now we have to say, well, what's our conclusion? So remember that our rejection region, negative 1.96 and positive 1.96. So anything in this area or this area was going to be a reject. So our conclusion then, step 6, our statistical conclusion is to reject. Okay. So now we have to step back and think more abstractly about our original problem. What does this mean for a managerial conclusion? Okay, so we can say that the mean is not 30 millimeters. Okay, and so we can see there might be a problem here with specification. You know, we're not meeting specifications, so there's some kind of quality issue going on there. Okay, all right, so there's the critical value method where you're just deciding, you know, does something, you know, does my test statistic fall outside my critical value is, you know, is one way to do it. So that 6-step procedure is just specifically for the critical value method. I want to say just a little bit about the other method, the p-value method. It's not terribly different. And if you look at my video finding p-values, that will explain most of it. But I just want to show where the steps actually differ when you're doing the p-value method. So notice that, so this is the p-value approach to hypothesis testing. Notice that we still start off stating the null and the alternative. We still choose the significance level and the sample size. We still have to determine the appropriate test statistic. Remember, it's in our case Z or T, depending on what the problem is. And sampling distribution, so this is normal or T. Collect the data and compute the value of the test statistic and the p-value. Okay, so this is where it differs, and the p-value. So before we had a step in here where we found out what those borders would be beyond which we would reject. In this case, we notice we don't determine those ahead of time. We first have to compute the value of the test statistic, and then we have to see, well, what's the probability? So the p-value, and if you don't know what a p-value is, you should see my video on finding p-values. The p-value tells you the probability of observing a value that extreme if the null is true. So probability of having something this extreme if H0 is true. Okay, so you can see if the p-value winds up being low, so if I have like a p-value equal to 0.0002, what this is saying is that if the null is true, we would only see this 0.0002% of the samples. So this is extremely unlikely, so therefore we have a lot of evidence to say that the null hypothesis is not true. We reject. Okay, so if the p-value is low, the null hypothesis must go. I think that's how your book puts it. Okay, and so this is what differs. So that's the step that differs, and so we have one fewer steps here. That is, we go in step 4. We do the value of the test statistic and the p-value, and then what we have to decide is, well, is the p-value less than alpha? Okay, so remember, if we say our alpha is 0.05, then if we have a p of less than 0.05, then we reject. So in our alpha here, under the critical value method, the alpha was used to determine where the critical value was. And in the case of the p-value method, alpha is being used to compare the magnitude of the p to see if that has met your standards for how sure you want to be. Okay, and then in step 5, exactly the same. You make the statistical decision and state the managerial conclusion. Okay, so here it is. If the p-value is less than alpha, reject. Otherwise, you don't reject. And then again, you have to state the managerial conclusion. Okay. Okay, so just to show real quick how that difference would work in our example, once again, the first step is going to be the same. Our hypotheses don't differ. Okay, and number 2, then we were accepting an alpha of 0.05 and a sample size of 100. Okay, so in 3, we said we're still given a population standard deviation, so we're going to say that the sampling distribution will be normal, and we're going to calculate a z-statistic. Okay, z-statistic. Okay, so now here is where it differs. We have to calculate that z-statistic, and remember that we wound up with a value of -2. So it was computed exactly the same way, but we're not using critical values to make a decision. So we calculated the test statistic here, and we need to know, okay, what's the p-value of this? So we've got this. This is the value of the test statistic. How do we convert this into a p-value? Okay, so remember that this is just a probability, and the Excel function that brought us from a z-score to a probability, these were just the normal dist. Okay, so remember that in order to find critical values, we use norm_inv. So now we're going to use norm.dist. Okay, and now this is the actual value that we're going to put in. Okay, and then there's other parameters in there. So let's go ahead and put those in there. Okay, so we found -2. We want to find the p-value of our -2 test statistic. Okay, so it's going to be norm dist. Okay, and our x was -2.0. Okay, mean 0, because the test statistics are always expressed with reference to the standard normal distribution, and standard deviation of 1, cumulative of true. Okay, all right, so So that wound up being 0.023. Okay. So our p-value was 0.023. But there's a little bit of a trick here. Remember that we're doing a two-tailed test. So we could just as likely have gotten a value in either of these tails. So the p-value expresses the probability. If we're doing a two-tailed test, we have to use the probability of it having been in either of these tails. And so by putting only this -2 in here, we only picked up this tail. So we have to actually multiply this by 2. So, because this area will be the same as this area. Okay, so the p-value when you're doing a two-tailed test is going to have to be multiplied by 2. Okay, so this is going to be 0.046. Okay, now remember that our alpha, so our statistical conclusion, we want to know is p less than our desired alpha. And so our alpha was 0.05 and our p-value was 0.046, so therefore we can reject. Okay, so that's the same conclusion we had with the critical value method. It would be quite wrong if it wasn't. So we're going to reject the claim. And so finally the managerial conclusion is the same also, that the bolts are not, that they are not 30 millimeters as specified. Okay. So two different methods, critical value versus the p-value method. Now, there are two things that can go wrong with a hypothesis test, and I put them on this chart here. So let's go over the ways that it's possible to be wrong in your conclusion. Okay. Well, let's first let's think about, okay, well, what's the truth of the situation? So in the columns here we have this is the truth. Okay, this is the truth. And so if the truth is that the null hypothesis is true and we have failed to reject, then we're good, right? So this is good. We've made no error. Okay, so if the null hypothesis is true and we have not rejected it, then we've made the right decision. Okay, so there's no error there. Okay, another way to not be in error is if the null hypothesis is false and we reject, then that also is right, right? So we are supposed to reject a false null hypothesis. Okay, so whether we fail to reject a true or we have rejected a false, we have done the right thing. Okay, so these two boxes then are going to be when we don't make an error. Okay, but there are two different ways that we can make an error, and let's go over the first one, which is if the null hypothesis is true and we have rejected it. So this is considered to be pretty much the worst thing you can do. This of the two kinds of errors, this is a very bad one. So you have a null hypothesis that is true and you have found a way to reject it, then this type of error is called the type 1 error. Okay. Now remember that when we were deciding on alpha, we were deciding on an acceptable level of being wrong. So we said, okay, 5%, we're okay with a 5% chance of making an error. This is what this is. You're by setting alpha equal to 0.05, you are establishing that you're okay with a 5% chance of a type 1 error. Okay, so 5% of the time when you draw a sample, you can make a type 1 error, and you're expressing that from the outset that that's okay. Okay. Now, the other way that you can be wrong is if the null hypothesis is false and you have failed to reject it. So this is called a type 2 error. And the probability of this is just something called beta. We're not going to get into calculating beta or 1 minus beta. Um, and we don't have to calculate alpha because we just set that from the beginning. That comes from the actual mechanics and the risk associated with your actual test. Okay, so there's a lot of material there. Some we went over hypothesis testing in general, particularly on one sample tests, the critical value method and the p-value method. Okay,